Welcome to The Explainer. Today, we're jumping straight into what might literally be the most critical, state-of-the-art leap in generative AI right now. We are talking about teaching foundation models to finally, and I mean finally, understand the actual physical rules of the 3D world. It's called JoyAI-Image, Awakening Spatial Intelligence in AI. So, think about it. What does happen when AI finally understands 3D space? We're all used to Gen AI making these stunning high-def 2D pictures, right? But ask yourself, what happens when an AI actually understands the geometry, the depth, and the real 3D space those objects are supposed to exist in? What happens when it stops just painting flat pixels and starts actually comprehending physical reality? Let's start with Section 1, the limits of current AI. Right now, we're hitting a pretty frustrating wall. The industry is kind of stuck with these task-specific pipelines. You've got one model for understanding an image, a totally different one for generating it, and maybe a third for editing. Because they're separate, they have really weak task interaction and, honestly, remarkably poor physical awareness. The holy grail here is a unified visual intelligence. We want strong cross-task coordination and deep 3D physical grounding. Which brings us to Section 2, introducing JoyAI-Image. Enter JoyAI-Image. Look at the precise geometry-aware transformations happening here. This demonstrates multi-view generation that actually maintains consistent spatial logic from totally different angles. It literally knows that if you rotate an object 90 degrees, the shadow and the structure have to behave according to the actual laws of physics. No more weird melting perspective issues. So the absolutely crucial takeaway is that JoyAI-Image brings its core functions, visual understanding, text-to-image generation, and instruction-guided editing together into one single foundation. But the real magic? It's this bidirectional loop. Enhanced perception and generative editing are constantly feeding into each other. Better spatial understanding creates more accurate image generation, and then those geometrically perfect edits feed right back in to make the model even smarter. It's brilliant. Let's pull back the curtain in Section 3, inside the unified architecture. To grasp how this continuous loop even works under the hood, we can break it down into two main components working in perfect harmony. Just think of the MLLM, the Multimodal Large Language Model, as the cognitive brain for scene parsing. It understands your prompt and analyzes the spatial scene. Then you have the MMDT, the Multimodal Diffusion Transformer. This acts as the generative engine for synthesizing images, taking the brain's thoughts and turning them into high-fidelity pixels. When we look at this unified architecture, notice how the cognitive brain acts as the ultimate shared interface here. It extracts incredibly rich semantic and spatial cues from your instructions, like, say, knowing a subject is exactly 1.7 meters away from a pillar, and then it directly feeds that into the MMDIT generative core. So it's not just text guiding the image anymore, it's deep spatial reasoning guiding the generation. That's a huge shift. Moving on to Section 4, Awakening Spatial Intelligence. Okay, so here is the million-dollar question. How on earth do you teach a flat 2D neural network about physical space? Well, the researchers built the Open Spatial Engine. Check out how it overlays these 3D box-centric meshes onto a real-world room layout. It's literally mapping the room, placing a precise 3D box around the bed, the cabinets, the sofa. It provides the AI with rigid geometric anchors so it finally stops guessing and actually starts measuring. But doing this by hand or relying on expensive 3D room scans, that's just not scalable. So to scale this up, they came up with a really genius 3D lifting mechanism. Step 1, they ingest millions of unconstrained everyday web videos. Step 2, they extract these 3D-oriented bounding boxes via 3D lifting directly from the video frames by tracking objects as the camera moves. And Step 3, they map those to frame-level object attributes. It totally bypasses the need for labor-intensive 3D scans. This automated data engine ultimately produced the massive open spatial dataset. We're talking about over 3.3 million fine-grained spatial entries. That's enough to cover everything from depth and distance estimation to multi-view consistency and camera perception. It is, quite literally, a massive textbook on physical reality for the AI to study. Which leads us nicely into Section 5, the art of data curation. Scaling up is great, but in AI, garbage in means garbage out, right? To stop the model from rendering that weird alien gibberish text we're all used to seeing, they implemented incredibly strict filtering rules. Accurate, text-faithful captions, they get a green checkmark and enter the dataset. But if a training image has a sign and the caption hallucinates a translation or misses a word, it immediately gets a red cross and is thrown completely out. To automate this level of quality control, they built this OCR conditioned caption generation and post-filtering pipeline. OCR, or optical character recognition, basically acts as an eagle-eyed inspector that extracts every single piece of text in a scene before the captioning is even written. It forces the captioning model to be 100% faithful to the source signage and languages, which drastically cuts down on the AI learning bad habits.
And guys, the payoff is absolutely staggering. Look at this advanced text rendering. We're talking web-grade typographic fidelity across dense digital UIs, beautiful text on coffee bags, and even complex multi-panel comics. And it handles all of this without a single hallucinated letter. Because it truly understands both the 3D space and the text within it, the final output is just pristine.
Okay, let's wrap this up with Section 6. Beyond general visual competence. So, what is the final verdict when we put all this to the test? Well, the benchmark numbers are crystal clear. JoyAI-Image hits a state-of-the-art 64.4 spatial average score across rigorous evaluations. That means it exactly matches elite proprietary models like Gemini 2.5 Pro, and it significantly outperforms GPT-4o, which sits at 57.7. That is a total game changer. Ultimately, what you should really take away from all this is encapsulated perfectly in this quote from the researchers. They say, "These results suggest a promising path for unified visual models in downstream applications such as vision, language, action systems, and world models." Essentially, teaching AI the physical rules of geometry isn't just about making cooler pictures. It is the absolutely critical stepping stone to full world models, digital brains that actually comprehend how our physical universe operates. Which leaves us with this incredible, maybe even a little provocative thought. If AI can now accurately reason about the 3D world, are vision, language, action robots next? If these models truly understand 3D depth, physics, and spatial reality, are physically intelligent robots literally right around the corner? It certainly seems like the foundation has just been laid. Thanks for hanging out with me for this explainer, and I'll see you in the next one.